Welcome everyone. This is a vibration Prac, and this is the mechanical system that we will analyze in this Prac. The objective of today's Prac is first we will discuss about the single degree of freedom system, which will start with the free vibration, and then we will go to the force vibration, and we will see how this system behaves under force vibration. Then we will add additional mass and spring to make this system as a 2 degree of freedom, and then we will see how that system behave under force vibration. So, there are 4 important elements that we need to focus for this mechanical system. First is beam, and then the second is spring, third is the exciter unit, and the fourth is revealer joint. There are hypotheses for each element. I will start with the beam. So, for beam we will consider this is a slender rod, and also we consider the mass is uniformly distributed. The second one is the spring. For spring we consider this there is no mass for this spring. So, we ignore the mass of the spring, and we consider the spring is a linear spring. Third one is the exciter unit. For exciter unit, the assumptions are exciter unit is a point mass, and when it operates, that means when it rotates, it has centrifugal force. Finally, the revealer joint. For the revealer joint, we consider it has only one motion. It has motion. It has motion in only one plane, and it doesn't have any friction. Alright, so let us draw the diagram of the mechanical system. So, this is a revealer joint, this is exciter unit, which is a point mass we consider, and this is the spring. So, let us consider the mass of the beam as MB and mass of the exciter unit as ME. The stiffness of the spring is K, and the length of the beam is capital L. The distance between the revealer joint to the spring is B. If that is the case, then we can write down the general equation for this system as J equivalent theta double dot plus K T equivalent theta equal 0. So, why this right hand side is 0? Because this is a free vibration. So, for free vibration there is no external force applied on this system, and that is why this right hand side is 0. If this is a homogeneous equation, the solution of this system to find natural frequency will be omega n equal square root of k torsional equivalent divided by j torsional equivalent, and this is our first task. This is our first task to find the natural frequency of this system. Okay. That means we need to find K equivalent and J equivalent. Alright. So, to find K equivalent and J equivalent equation for this particular system would be L square by 12 times 4 MB plus 3 ME. And for K equivalent, the expression is K average K times B square. So, we can understand to find the natural frequency of this system, we need to know J equivalent and K equivalent, and to find J equivalent and K equivalent, we need to know L, we need to know mass of the beam, mass of the exciter unit, and the distance between the revealer joint and the spring. Also, we need to know the average stiffness of the spring. Alright. So, for J equivalent, we need L, we need MB, ME. So, in the problem or in the system, you are given these value, which is the combination of the beam and the exciter unit. So, for finding J equivalent, we need L, we need MB, ME, and for this system the combination of beam and the exciter unit mass is given to you as 2.415 kg. All right. So, you can understand, definitely you need to find MB and ME separately to get J equivalent. All right. So, if we consider the material of the beam is steel, then we can find the density of the steel, which is very normal general density, is 7750 kg per meter cube. Now, you will give the beam to you so that you can measure all the dimensions, and if that is the case, you can definitely measure length of the beam, height of the beam and width of the beam. And then definitely combining these three, you can measure or you can get volume of the beam. If you know the volume of the beam, then definitely you can find mass of the beam as density times volume of the beam. So, we have MB plus ME, and just few minutes ago we find MB. So, we can easily find ME, and we can find L. So, using this 3 value we can find J equivalent. Now, for finding K equivalent, we just need to know this average spring stiffness and the distance between the spring and the revolute joint. This value you can use ruler and find this value. So, to find the average K, which is a spring stiffness, will give you 3 masses M1, M2, M3, and we need to get elongation of the spring for 4 cases. One is without mass, which will consider static elongation of the spring. Second one respect to mass 1, third one is respective to mass 2, and the fourth one is respective to mass mass 3. And then we take the difference between these elongation, which gives us x1 minus x0, x2 minus x0 and x3 minus x0. Then we want to get the force for these masses, which is M1G, M2G and M3G. Now, from the definition for linear spring, we know that K equal force divided by the elongation or displacement for the spring, which we can write as del x, and this is our del x, this is the mass. So, we can, and this is our force. So, we can find K for these cases as M1G divided by this del x, which is x1 minus x0, and we can do same way for other 2 cases. Let us just consider K1, K2 and K3. So, once we get these 3 values, we can take average of these 3 and that would be our result to use in this equation. Now, for the lab, we will use this value to calculate natural frequency, but when you have all the data, then you need to plot this information on MATLAB, and using the MATLAB code you need to use spring average stiffness, and that you need to use in your report that spring stiffness. All right, so we will dismount this system now. So first dismount the spring. Alright, so we'll start with measuring the length of the beam, which is from end to end. So the length of the beam is 73 millimeter, which, by the way, all the dimensions measured here are given in table 3. So you can have a look there. The width of the beam is 25 millimeter and the height of the beam is 12 millimeter. Okay, and then we need to also measure the distance between the revealer joint and the spring. So the revealer joint was connected here and the spring was connected here. So we need to measure the distance from the center of this hole to center of this hole. Okay, so to do that, I'll just measure from there, from the center of the hole, so from the center of the hole that gives me 650 millimeter. Okay. Yeah, and then with this one, if you can remember, this is a unit, exciter unit. So this exciter unit will consider when we consider the system is under force vibration. Now when the system is under force vibration, this exciter unit rotates, and when it rotates, it has eccentric mass that also rotates. So can you see this small piece of metal? This is eccentric mass. The mass of the eccentric, this eccentric mass and the distance from the center of the beam to the center of the eccentric mass are given in the table 7 of your handout. So you can just look at table 7 for that. So to get the spring stiffness, average spring stiffness, first of all we need to measure the elongation of the spring for 3 different masses. Okay. So the elongation that I will take for spring, even though we are attaching this attachment, but we'll ignore the mass of this attachment, and the elongation for the spring that we measure would consider a static elongation of the spring. To get the static elongation of the spring, first we need to measure the elongation of the spring or the length that spring elongated. Now we need to very lightly touch this surface, and then first we look at the larger scale. The value, 0 value on the small scale, when it crosses the number we take that number. So in this case it's 63. So we'll take the 63, and then because this 0 value does not match the with these lines exactly, so to get the exact value or to get the fraction of this scale, we'll look at the smaller scale and look for the line that exactly matches with these lines. Okay, so So our value is 62, and then look for the exact value. Now if you just look at 7, it exactly matches with this line. So the value or the elongation of the in that situation, the value would be 62.7 millimeter. Okay. Then we'll add mass. So for measuring the spring stiffness, we'll consider 3 masses. The first one is 1 kilo. So I'm adding 1 kilo to the system or attachment, and then exactly same way we'll just touch lightly and then look for the value. Now in this case it looked like 69 millimeter. So referring to table 4, all the values are given. So for 1 kg, the spring elongation is 70 millimeter. Then we'll consider the second mass, which is 2 kilo. For 2 kilo mass, again we'll measure the elongation of the spring, following the same procedure. In this case, this value is 75.7 millimeter. And finally, for 3 kilo, the value is 82 millimeter. So the solution of this general equation would be sine, let's say sine component. Okay. So let's just draw the sine component, right, where this is time and this is amplitude. Now that means theoretically we are expecting the system that I draw here would respond like a sine wave or cosine wave. Okay, that means the amplitude will be same. Okay, and if this is the case, then we can measure frequency of this curve by following this equation, which is frequency equal number of cycles divided by time. Okay, so if we measure in 1 second, just counting the number of cycles, we get the frequency in hertz, which is the unit. Okay. So that means from these equations and from this diagram, we can expect the system, free vibration system would behave like this. That means once it vibrate continuously. So now to get the comparison between the theoretical natural frequency and the calculated one, we'll use this accelerometer to measure the vibration of this system. And then if you just look at this window, this horizontal axis represents time, the vertical axis represents amplitude in millimeter. So we'll get idea from the natural we'll get idea from this window the frequency of this system, and then we can compare the calculated one and get the percentage of error between these two natural frequency. Even though this is a free vibration, but still we need to disturb the system initially. Okay, so I'll just disturb the system. Okay, and then just look at this two window, and then I'll pause. Now I'll pause here. First of all, this window is for 1 second, this window is for 10 seconds. If you can remember, we theoretically expected that the system will behave like a sine curve. That means there is no reduction in the amplitude. However, if you just look at this window, it reduces a lot. Okay. And also if you can just look at this system now, it is stable at the moment. Okay. That means this diagram and the physical system you can see match. Okay. So, that means even though there is no physical damper attached to this system, but there is a natural damper present in the beam, and that is why even though the system was disturbed, eventually that disturbance makes the go away and the system becomes stable. Okay. Now, let us just measure the frequency of this system, natural frequency of this system. So, if you just look at this 1 second window, now we know the number, to find the natural frequency, it is number of cycle divided by time. So, time is 1 second. So, if we just count the number, that would give us the natural frequency. Okay. So, 1, 2, 3, 4, 5, 6, 7. Actually, it's if you can just look this 3, 4 and close to 7, but it is not completely 7. We can consider this as 6.5. So, that means the system or the experimental natural frequency of this system is 6.5 hertz. Now, we can compare this frequency with the calculated one and we can find the percentage of error. All right. Now, when we consider the system is under force vibration, then we need to consider the exciter unit, and if you can remember, I showed you the eccentric mass in the exciter unit. So, when the exciter unit is operating, there is a hypothesis which says that the force that acting on that exciter unit is centrifugal force. That means the force is acting this direction. Let us say we denote that force as Fc, and it is acting at an angle capital omega t. And now, with this eccentric mass, let us denote this as m epsilon, and the distance from the center of the beam to the center of the eccentric mass can be denoted as epsilon. This mass and the distance epsilon both are provided to you in the Prac instruction sheet. Now, with the omega t, this capital omega is the angular velocity of the exciter unit. Also, we can consider this is the force frequency applied to this system. Okay. So, if we just draw this portion here, which is Fc, centrifugal force, is acting at an angle capital omega t, then we can understand it should have, this force should have two components. One is horizontal, which we can denote as Fc cos capital omega t. The other is vertical component, which is Fc sin capital omega t. Now, what does this horizontal component and physical and the vertical component physically mean? Let us just go back to our system, mechanical system, and there I will explain it. Okay. So, if you just look here, the horizontal component which says Fc cos theta, that part of this exciter unit is cancelled out with the horizontal part of revolute joints, and for that reason when we disturb the system does not move in horizontal direction, it only moves in vertical directions. That means, to analyze this system, we need to just consider the vertical direction of the system, which is Fc sin omega t. Now, to write down the governing equation, general governing equation of this system, we can write J equivalent theta dot dot, which is acceleration, kt equivalent theta equal the force that is acting on this system, which is this one. So, Fc sin omega t times the distance. So, from revolute joint to the exciter unit, the length is L by 2. So, we can multiply L by 2. That means, this is a moment. We are considering the moment here. Alright, so that is the general equation for force single degree of system. Okay. Now, this equation is a non-homogeneous equation. If it is a non-homogeneous equation, the solution should look like theta equal theta h plus theta p. Theta h means homogeneous solution, theta p means particular solution. For homogeneous solution, which is referred to the free vibration. So, for free vibration, if you can remember, once we disturb the system's amplitude damps out. That means, after a while this part will be cancel out. The only part that will acting on the system will be theta p. That means particular solutions. So, for force vibration system, we need to consider particular solution. To get the expression for particular solution, I will write the equations here. Should I just theta p equal capital P, which is the amplitude, times sine capital omega t. So, that is the particular solution for this system, where theta p, capital theta p is the amplitude and sine omega t. That means, we can understand the response of this force vibration system would be a sine curve. We know the pattern of the curve, we just interested about the amplitude of this equation. So, to consider the amplitude of these equations, first write down the expression of the amplitude, which I get. Now, I will erase this part and then write down the equations. The expressions of amplitude of theta p can be written as m epsilon capital omega square epsilon capital L divided by 2 k T equivalent divided by 1 minus capital omega square divided by omega n square. Alright. So, this bit it's pretty much constant for particular system. The only thing change is the omega or the force frequency. Alright. So, let us consider 3 cases. So, let us consider when omega equals to 0, when omega equals to omega n, and when omega tends to infinity. When omega equals to 0, that means there is no external force applied to the system. What would be the value of theta p here? When you put this value here, the amplitude should look like 0. That means, we do not get any vibration, there will be no amplitude. Okay. The second part is, let us consider when the force frequency is equal to the natural frequency. What would be the value for theta p? If we substitute these values here, then the expression should look like this. That means infinity. Okay. So, that means, when force frequency is equal to natural frequency, the amplitude should be infinity. And the last one, where force frequency tends to infinity, that means really big number, then the amplitude of that expression would be constant. Important thing is that this amplitude will not be 0, it should have some value. Okay. So, if we have these 3 values, let us just try to draw this diagram theoretically. So, this is capital omega in hertz, that means this is the force frequency and this is the amplitude of particular solution theta, capital theta p in let us say millimeter. Okay. So, if we just consider this bit, so it should be here 0, at 0 omega theta p is 0. Then let us say this at this point capital omega is equal to omega n. So, the amplitude would be infinity. So, the curve should look like this. Okay. Just draw it again here. And the last one, when the capital omega is tends to infinity, let us say this is a really big value, at that point the curve or the amplitude would look like should have some value, but it definitely will not be 0. So, that is our expected curve from this expression. Now, we need to see from the experiment how the system really behave. All right, to get the experimental data, I am just referring to the table 6 of your handout, where you need to first fill up the first column, which is the frequency of the exciter that we get from these function generator. I will turn it on and I will just change the frequency, and you can see the frequency is changing. See, the frequency is changing. Okay. So, to fill this column up, we will start from 5 hertz, and then we will try to do it every hertz, that means 5, 6, 7, 8, 9, 10, 11, 12, and then we will jump to 20. Okay, that is where we fill up this. The second important thing to remember to fill this table is the third column, where it says frequency of the beam vibration. Okay. Now, my question is, if you apply this external frequency which is coming from here is 5 hertz, what would be the frequency for this beam? Okay. We will first check with the system. Once we are happy with the system, then we can fill these column exactly or accordingly. All right. The second important thing in this table is the fourth column, where you need to measure the maximum amplitude, and to measure the maximum amplitude you need to focus on this window, where you need to just look at the maximum amplitude. For example, at the moment the maximum amplitude was 0.404 millimeter, and then you need to write 0.04 millimeter here. Okay. All right. So, let us start with the first force frequency, which is 5 hertz. So, I will change the system to the 5 hertz. There you go. So, this is a 5 hertz. Okay. Now, at the 5 hertz frequency, you can see this is the beam started to vibrate, and we want to, I will just pause here first. Then we want to first fill up the third column, which is the frequency of the beam that I asked you. Let us just check what would be the frequency of the beam. If you just look at this window and count the number of cycle, it is 1, 2, 3, 4, 5. That means I applied 5 frequency to the system, and the beam is vibrating at the same frequency. Okay. That means if you can fill up the frequency first column, which is the frequency of the exciter unit, then you can exactly fill up same way for the third column, which is frequency of the beam vibration. Frequency of the exciter unit and frequency of the beam vibrations are same. We can see from here. All right. And the second important thing is that what is the maximum amplitude you get at 5 frequency. The maximum amplitude you get for 5 frequency is 0.042 millimeter. Okay. So, that means on the fourth column, the first value would be 0.042 millimeter. Okay. So, that is our first case, and then I will just unpause it again, and then I will change it to 6 hertz. you can see that with the increase of exciter frequency, the beam started to vibrate more and the amplitude also increased. The amplitude at the moment is 2 millimeter, where for 5 Hz it was 0.042 millimeter. Okay. Now I'll just very slowly increase the value. Okay, I'll just very quickly pause here and then move it. So, can you see that first of all, at this point the system behaves drastically. The amplitude was huge, 7 millimeter, okay, and you can see the system was vibrating huge with the huge amplitude. Now, the frequency that we get that kind of behavior was 6.5 Hz. Okay, that means at that point natural frequency and the exciter frequency are equal. That's why we get the highest amplitude, and that phenomenon that we already just saw is called resonance. Okay, so when the natural frequency of any system and the exciter frequency are equal, you will get a huge amplitude and it could destruct or damage the system. Okay. So, we can find that the natural frequency of this system actually is 6.5 Hz, and that is why at 6.5 Hz we get the highest amplitude, which was the resonance. All right. Okay, I'll then move again. So, I'll pass this natural frequency and then now it's 7 Hz. Once we pass the natural frequency or the resonance state, you can just look at the system. It is vibrating, but not like the at resonance frequency. And again, the amplitude is here is 3 millimeter, around 3 millimeter. Okay. I'll increase the frequency more. At 8 Hz, the frequency amplitude, the vibration amplitude is around 1 millimeter. So, you can see that once we pass the resonance state, the amplitude started to decrease again. Okay. At 9 Hz, the amplitude reduce even more. Now, the amplitude is 0.8 millimeter. Okay. All right, exactly same way we will do for 10, 11, 12, and in those three frequencies the amplitude will remain small amount. Okay. Now, I will quickly jump to the very big number, which is in the explanation I said that when capital omega it tends to infinity, in this time we will jump to the big number as 20 Hz and we will see how system behaves. Okay. Let us jump to the 20 Hz, which is in the explanation I said capital omega is tends to infinity. You can see that even at 20 Hz, which is really high frequency, first of all the beam is not vibrating much. And if you just look at the amplitude is 0.4 millimeter. Okay. That means it does not go to 0, at the same time it is not as high as resonant frequency. Okay. And that is how we end this part of our vibration Prac. Okay. So, two important things from this task is that for single degree of freedom system, we have one natural frequency and that is why we get one resonance. And once we avoid that resonance frequency, then we can apply the even higher frequency without damaging the system. Okay.